PT आता इकडे जायचं ना मेजर पॉइंट्स applications. Hello and very good morning. Wherever you are, I am W.K Gagare. Let me welcome you to this course, whose title is Laser Application. This course has basically intended for undergraduate students, FYBC, Physics Paper Second, Physics Principle and Application, Chapter Second, Laser and Laser Applications. In 1917, Albert Einstein established the existence of stimulated emission in a black body radiations. This concept of stimulated emission given by him becomes the backbone of laser physics. Today, the word laser is familiar to everyone due to various applications in medicine, communications, industry, defense, almost everything. Laser is one of the outstanding inventions in the 20th century. Laser is a device for producing very intense, almost unidirectional, monochromatic and coherent light wave. Uh, then lasers, objective of lasers. Then objective of lasers is properties of lasers. Then basic principle of lasers. Then lasers outcomes laser absorption, spontaneous emission and stimulated emissions. Characteristics of lasers beam: monochromaticity, second directionality, third coherence, fourth temporal coherence and brightness and divergence. Monochromaticity: if light coming from source has only one frequency wavelength of oscillation, the light is said to be monochromaticity. Directionality. Direction, conventional light source emit light in all direction, but laser light emit in only one directionality. And coherence means all photons has the same phase is a coherence. Temporal coherence and brightness intensity is very large and remains constant with a distance, and a very little divergence of laser beam. Then introductions of lasers have truly been one of the greatest inventions in 20th century. They have found a variety of uses in electronics, computer hardware, medicine, industry, military and experimental science. The laser stands for light amplification by stimulated emission of radiation. Laser is a device that emits light through a process of optical amplification based on the stimulated emission of electromagnetic radiation. A laser differs from other sources of light because it emits lights coherently. And see the pictures below of the laser beams here. Then properties of lasers. Also the same as directionality. Coherence means coherent light. The diagrams here. Then monochromatic. There's single source here. Then structure of atoms. Atom consists of central nucleus consists of proton, neutron. Around is the electron is revolving the number of orbits: first orbit, second orbit, third orbit. N is 1, first orbit state, energy is 1. N is 2, second orbit state, energy is 2. And third orbit state, N is 3, the nucleus. Electron revolve around this. Protons is equal to electron, therefore atom itself is a neutral. The structure of the atoms here. Then the principle of laser action. The principle of laser action is based on four separate features: absorption, then spontaneous emission, stimulated emission. This is the fourth one. Then first one, Absorption. In absorption, an incoming photon excites the atomic system from a lower energy state into higher energy state. It occurs when a photon strikes an atom with just exactly proper energy to induce an electronic transition between two energy states. Diagram shows the below absorption of radiation or light during absorption. During absorption, low energy state and higher energy state. A photon earlier absorbs an ground state energy and electron absorbing photon energy, therefore they goes to the higher energy stage. After absorption, higher energy state electron jump to the excited state after absorbing photon energy and goes to the lower energy states. Suppose a photon of energy hν is incident on an atom in energy level E1. The photon is absorbed by the atom and it jumps to excited state E2, raising or pumping of atom from lower to higher energy level through the process of absorption of light is known as optical pumping. One photon disappears from the incident light and one atom is added to the excited state. Therefore, H plus hν, this becomes A star. A star in excited atoms states. And the second one is spontaneous emission. It takes place when an electron in a higher energy level drops down to the lower energy level and a photon is emitted with an energy equal to the energy difference between the two levels. Diagram of spontaneous emission. Before photon emission, higher energy state, lower energy state. Electron in excited states. Excited state electron are realizing photon during transition higher to lower energy states and goes to the lower energy state, and therefore this emission of the photon and randomly this spontaneous emission. The process is represented by A stars is equal to AI plus hν. Features of this one. Spontaneous emission cannot be controlled by outside. It is usually probabilistic in nature. The light spreads in all directions around the source. The light is incoherent. The light is monochromatic. Stimulated emission. It takes place when a photon with an energy equal to the energy difference between two levels interacts with the electron in the higher energy level. Stimulated emission. Before photons emission, in a higher energy state is present electron, excited state electron absorbing photon energy, and excited state electron releasing two photon during transition higher to lower states. Therefore, this photon emission during transition and this emission of the two photons and electron goes to the lower energy state. This is a stimulated emission. The process is represented by A star plus hν is equal to A plus twice hν. Features. Stimulated emission can be controlled from outside. The photon in this process propagate in the same direction as that stimulating photon. The emitted photon has exactly the same frequency, phase and plane of polarization as those of the incident photon. Multiplication of photons, light amplification. The population inversion. Fourth one is population inversion. Is when more atoms are in the excited state than in their ground states. It is a necessary condition to sustain the laser beam so that there are enough excited atoms that can be stimulated to emit more photons. To achieve non-equilibrium condition, an indirect method of populating the excited state must be used, which is done using three level laser and four level lasers. And then diagram first shows that this is a E1 first state, E2 second state, E3 in excited states. Photons in here goes use the energy of these electrons and this goes to the higher states here, and therefore this increase in the higher state level is electron. This we call as optical pumping. Figure diagram shows the second one. Then figure 3 shows that in higher states, in a short time period of this living there, this goes to the lower states, and this is those we call metastable states. In metastable states, there for this emission of this layer is we call. And after that, this comes to this we call this is a population inversion. Population inversion nothing but more electron present in higher state to than the lower states. In these states, types of lasers. Laser is device that emit light through a process of optical amplification based on the stimulated emission of electromagnetic radiation. Gas lasers. Example helium-neon lasers, liquid laser expression, semiconductor diode lasers, solid state lasers, and ruby lasers. Only the study of the two lasers here, gas lasers and solid state lasers. Uh, See the diagram here. Okay, helium neon laser. Helium neon laser, usually called helium neon laser, is a type of small gas laser. Helium neon lasers have many industrial and scientific uses and are often used in a laboratory demonstration of optics. Helium neon laser is a four-level laser. It is usually operation wavelength is 632.8 nanometer in the red portion of the visible spectrum. It operates in a continuous working mode. Continuous working mode. Construction of helium neon laser. The setup consists of a dish to populate 80 centimeter and a bore diameter of 1.5 centimeter. The gain medium of the laser, as suggested by the name, is a mixture of the helium and neon gases in 5 to 1 to the 20 to 1 ratio, contained at low pressure and average 50 Pa per centimeter of cavity of lead in a glass envelope. The energy or pump source of the laser is provided by an electrical discharge of around 1000 volt through an anode and cathode at each end of the glass tube. A current of 5 to 100 milliampere is typical for CW operation. The optical cavity of the laser typically consists of a plain high reflecting mirror at one end of the laser tube and a concave output coupler mirror of approximately 1% transmission at the other end. Helium neon lasers are normally small with cavity length of around 15 cm up to 0.5 meter and optical output power ranging from 1 milliwatt to the 100 milliwatt. Then construction of helium neon laser. This is a gas envelope. Gas envelope is a air filled with helium-neon gas reservoir. One ear the this called one end of this called is anode, another end of this is cathode, and this proportion high reflected of this one. This is output coupler and laser. Here this is used as a laser output. The diagram shows this construction of helium neon lasers. Simplifying. Working of this one, helium neon gas laser. Description of the rather complex helium neon excitation process can be given in terms of the following four steps. First steps, when the power is switched on, an energetic electron horizontally excites of helium atom to the state level 2-1s. Helium atom in this excited state is often written as helium star 2-1s, where the asterisk means that the helium atom is in excited state. B. The excited helium star 2-1s atom collides with an unexcited neon atom, and the atoms exchange internal energy with an unexcited helium atom and excited neon atom, written NAS or N star 3s resulting. This energy exchange process occurs with the high probability only because of the accidental near equality of the two excitation energies of the two levels in these atoms. Thus, the purpose of population inversion is fulfilled. Diagram shows that here this is the E1 state, E2, E3, E4 and E5. This is energy states and they are helium atoms here. This is neon atom. And this 3 to 5, this we call this higher state is the metastable states here. And it produces population energy needed for a lasing action here. Here is a collision with an excited helium atom here collision, and this neon goes to the E5 state to the E4 3.391 microns. Also neon goes to the E2 states here, so it is emitting 632.8 microns here, then goes to the like that, this is 1.152 microns, this E3 to E1, and then E2 to E1 is a spontaneous emission and goes to the again ground states, energy states here. The diagram. Description of energy level diagram. When the excited neon atom passes from metastable state 3s to the lower level 2p, it emits photon of wavelength 632 nanometer. This photon travel through the gas mixtures parallel to the axis of tube. It is reflected back and pulled by the mirror ends until it stimulated an excitation. Helium atom and causes it to emit a photon of 632 nanometer with the stimulating photon. The stimulated transition from 3s level to 2p level is a laser transition, and this process is continued, and when a beam of current radiation becomes sufficiently strong, a portion of it escapes through partially silver dead. The neon atom passes to the lower level, is emitting spontaneous emission, and finally the neon atom comes to the ground state through collision with the tube while and undergoes radiation less transitions. Less transition application. The narrow ray beam of helium-neon laser is used in a supermarket to read barcodes. The helium-neon laser is used in holography in producing the 3D images of objects. Helium-neon lasers have many industrial and scientific uses and are often used in laboratory demonstrations of optics. Second one is Ruby laser. Introduction of the Ruby laser is the solid state laser. Ruby laser is the first successful laser developed by my man in 1960. Ruby laser construction. Ruby laser consists of cylindrical rod, optically flat and accurately parallel. One end fully silvered, other is partially silvered. Ruby rod surrounded by a glass tube surrounded by a helical xenon glass tube acts as an optical pumping scheme. Optical pumping scheme. The diagram shows here helium-neon pump. This gives you as a flash lamp gives you as an optical pumping scheme here. Ruby lasers rod here 5 to 10 millimeter, and this connected as power supply, high power supply, and the silver mirror coating here is present, and this gives out here laser here output here. This is diagram of ruby lasers. Mm, then ruby or aluminum oxide Al2O3 doped with 0.05% of chromium oxide Cr2O3. The aluminum atoms in the crystal lattice replaced by the Cr3 plus and Cr ion excited from level E1 to E2 by absorption of light by wavelength 550 nanometer from the xenon class tube. Excited ion is a non-radiative transition with the transfer of energy levels. A2 metastable state lifetime is 3 into 10 raised to minus 3 second. Population of E2 level greater than the level E1. Population inversion is achieved here. Population inversion achieved. Some photons produced by a spontaneous transition from E2 to E1 wavelength 694.3 nanometer. Ruby rod acts as a reflecting mirror. Photons not moving parallel to the ruby rod but are reflected back and forth. This stimulated the emission of similar other photons. Energy level diagram here. This is the E0 states, is ground state, E1 state, upper state, and E2 and excited states. And therefore, this 5 layers pumping is gives a lower state to the higher states for 400 nanometers. This is first one, and this is second stage gives you 550 nanometers. And here radiation-less transition from this, not radiate anyone this stage here, radiation-less transition, and goes to this state here is we call it metastable state, this metastable state, and therefore this emission of this stage. And here from this metastable states, this gives 694.3 nanometer laser is transitions. The diagram show here this one. Application of laser: scientific, medical, medicine, industries, commercial purposes, military, scientific, Raman spectroscopy, astronomy, astrophysics, geology, seismology, remote sensing, optical communications. Thank you very much for your attentions.